Okay, started. So we didn't go that far. So for any function, there's a power series. In fact, there's a sequence of the coefficients that you can, plug it in there and it gives you the corresponding power series. So you prove that in Calc 2, and it's very simple to prove. So it can be proved that it's basically algebra, that for any n, C sub n is this guy, is the nth derivative of f evaluated at a divided by n factorial. Okay, so you exactly can write any function as a summation of this power series. So for each n, derive the function to that order, evaluated at a, divide by n factorial. Those are the coefficients of the series. Okay. In fact, if you can remember, this was called Taylor series. Taylor series, of f of x centered at x equal a. Okay. Special case, if a is 0, then you can write f of x as nth derivative, all evaluated at 0, n factorial x minus 0, which is just x, right? So just x to the n, and from 0 to infinity. This one also had a special name. Does anyone remember what that name was? Taylor, and the other one was called Sosdam, Maclaurin. Yeah. Basically, Maclaurin is a Taylor series centered at 0. That's it. So, for example, let's write down power series for e to the x. Some of you might already know, and this is, how you can come up with this series. So simply, for f of x equals e to the x, I have a question for you. What's any order derivative of f? First derivative is itself, second derivative is itself. It's all e to the x, right? So for all of them, nth derivative of e to the x is the same thing. So if you evaluate it at 0, it's 1. Okay, so this one is simple. That means e to the x, according to this formula, is the summation n from 0 to infinity, 1 over n factorial x to the n. So if you rewrite it, it's going to be x to the n over n factorial, n from 0 to infinity. Do you remember that estimation I wrote up there? There you go. This one. That comes from that summation. So, e to the 3, when you punch it in the calculator, that's what it does. It starts with 1. By the way, this is, 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus so on. So it does 1 plus 3 squared over 2 factorial plus 3 to the third over 3 factorial, 3 to the fourth, 4 factorial, and so on. So you calculate this part, and that's a very good approximation of e to the third. Okay. So if you guys have your textbook, there's a table. So that's what I mentioned earlier. So page 605, that's basically the second page of 11.1. Like right in the middle of the page, there are 8, 1, 2, 3, 4, 5, 6, 7, and 8 power series. So you can use those wherever we need to. Okay. So I'm not going to write all of them down, but you can basically prove all of them by doing the same thing, except as long as you can find the formula for the nth derivative of a function, you can write a power series for it just like that one. Okay. Now, let me talk about two more things. Number one. Let me put it as a theorem. Okay. Make it a bit important. That's theorem. If this guy, using a sub n for the coefficients, so n from 0 to infinity, and summation b sub n x to the n from 0 to infinity. If these two are two power series, this operation, oh, thank you, Eli. So let me write down here. It says page 630. If this is 4th edition, that means that one is 3rd edition. Thank you. So if you have two power series, then we can add them. There's only one condition. The first element or the first counter, remember, this is basically the index of you counting the element or writing down the elements of this power series, of this summation, right? So this is telling you my first term in this series starts when n equals 0. So here, part one of this. Let me include that if both series start from the same counter, so here n equals 0, then we can add them. I'm trying to use it as simple as possible in our language to write this down. So, and this is how you add them. It's sort of you factor, x to the n. But again, the condition is that they both have to start from n equals 0. So in that case, you can write this, as a to the n, x to the n, b to the n, x to the n. And if these two are the same, sometimes it's not the same. We'll get, the examples like that. You can go ahead and write this as a to the n plus b sub n times x to the n, and starting from 0 to infinity. Okay, so I can put both series in one single one. Example. What's the power series for e to the x? It's 1 over n factorial x to the n, and starting from 0 to infinity. Okay, it's very simple to show that. In fact, let's write this one down. So I'm replacing this one, x, with negative x, okay? So let's replace, x with negative x. We're going to get that. Let me simplify it. So that becomes negative 1 to the n over n factorial x to the n. And it's starting from 0 to infinity. In fact, this one, all the terms are positive, right? You have 1 plus x squared over 2 factorial plus so on. This one alternates. Like the first one is 1, the next one is negative x, then it's plus x squared over 2 factorial. The next one is minus x 3 over 3 factorial, so on. Okay? Now let's add them. What happened? So e to the x plus e to the negative x equals summation of x to the n over n factorial. Let me write it this way. 1 over n factorial x to the n plus summation negative 1 to the n over n factorial x to the n. Both starting from 0 to infinity. Okay? They both start from the same thing. They also have x to the n as a common term. Okay? So we can put them in one single series where x to the n is factored. Both start from 0 to infinity. Here I have 1 over n factorial plus negative 1 to the n over n factorial. Okay. Now, we try to simplify it. We can stop right here, okay? But let's simplify it. In fact, I want to prove one of the lines in page 605. I have a question for you. If n is odd, what is this sum equal to? That's 0. Very nice, right? Because if it's odd, the denominators are the same, so the numerator of the second one is simply minus 1 of that one, so that's 0. And if n is even, you have 1 over n factorial plus, if it's even, of course, it becomes, plus 1, so you have 2 over n factorial, right? Now, since that's even, I can go ahead and write this as 2. In fact, n is 0, 2, 4, 6, 8, 10, and so on. So I can go ahead and write that n. That means n is some 2 sub 2k, right? That's how we represent even numbers. Odd numbers we are presented by 2k plus 1. Even numbers we are presented by 2k. So it's 2k factorial. Good? Okay. So that guy, simply, you can write it as 2 over 2k factorial x to the 2k, k from 0 to infinity. You okay with that? Okay. I'm going to go ahead and factor this 2 out because it's a constant. So I can do 2 summation x to the 2k, 2k factorial, k from 0 to infinity. And what did we start with? E to the x plus e to the negative x. So this equals to that guy. I'm going to divide both sides by 2. So I get e to the x plus e to the negative x divided by 2, which is summation. And this summation is as same as the same summation for any variable or for any counter that you put in the series. Like there's no difference between this guy and the one that I'm about to write down. X raised to the 2q factorial, q from 0 to infinity. The only change is this variable right here. So I'm going to go ahead and put it back as as n. So it's going to be x to the 2n factorial, and start from 0 to infinity. Okay. Now, we have a name for that. Does anyone know what's called? Yes. So we proved cosine hyperbolic of t has the power series of x to the 2n over 2n factorial and from 0 to infinity. And this is exactly line 4. 1, 2, 3, 4. That's the 4th line, 4th row on that table. So that's the 4th row, page 605. Every single one of them can be proved, same way. Anyway, that was just an example. So we said we can add 2 series. You can also multiply 2 series. I'm not going to mention it now. We don't have to. We can also divide 2 series. We don't need that one either. But here's one important. So that was theorem. That was part 1 of that theorem. So this is part 2. Part 2 of the same theorem. If you have a series, okay, and this series equals to 0 for any x inside, the domain of that series, in fact, I do need to talk about this one. So let me change my language. So for any x in the convergency interval. I'll explain what that one is. I'll put a question mark. I'll explain what that is. For any x in the convergency interval, this interval is symmetric. Probably remember how we got that. Like there was a radius of convergency. Okay. So for any x inside that interval, if this is true, then think about it. Is summation infinite sum is 0? This is only possible if then all a sub n, they have to be 0. I mean, this is a very trivial fact, and you might feel like, this is not even worth mentioning, but believe me, it does. So if you have a series, power series equals 0, every single coefficient has to be 0. So we set every single coefficient. So every coefficient must be 0. Okay? All right. Part 3 of that theorem. I mean, this is not a theorem, but it's very simple to. So it's called the change of the counting variable. I'll explain what I mean. Let's consider this one. Consider a sub n, okay, x to the n, and let's start n from 0 to infinity. I'm going to do something here, and you guys tell me if it's correct or not. So in this series, as you can see, I changed the index of n to n minus 1, and I changed the power of n to n minus 1. And also changed the counter. Here starts from 0. That one starts from 1. My question is, are these two series the same? Basically, if you expand them, do you get the same expression? Do you guys see what I'm asking? Basically, do these two series represent the same summation? The answer is yes. Yes. I mean, if you write it down here, since n starts from 0, you have a sub 0. You have a1x plus a2x score and so on. And the second one is the same, right? When you plug 1, the first element of that sequence is a sub 1 minus 1, which is a sub 0, and the powers is also x to the 0, okay? So it's going to be the same. Now, how did this happen? Basically, you're doing two opposite operations. How? And this is not mentioned, nowhere in the theorem. It's sort of considered as an obvious fact that if you add 1 to the counter, I add 1 to this counter. Equivalently, I have to subtract 1 from the, the counter inside the terms of the sequence. Do you see what I'm saying? So if you add 1 to the n, or subtract 1 from the n, or add 1 to the n, then inside here you have to change n to n minus 1. Let me do another example. Let's say I have a sub n, and here let's do n plus 2, okay? And then n starts from 3 to infinity. Okay. This is what I'm going to do. I would like to write a series that starts from 0. That's what my goal is. I would like to rewrite this series as a series where n starts from 0, not 3. Now, what should I do inside here? Well, since I subtracted 3, so from here to here, I subtracted 3. Okay, what do I do to the indices if I subtract it? You do the opposite. You add 3. Okay, so that means this index, wherever you see n, you replace it with n plus 3. So it's going to be a sub n plus 3. and then it was plus 2, but you're doing n plus 3, that means it's going to be n plus 5. Do you see what I'm saying? So if on the counter, whatever you're doing, on the terms of the summation inside, you have to do the opposite. So here you add 3 to all n's. We're going to need this when we combine series, and I'll explain when we will do this. Hopefully we can do an example today, and you'll see why we're going to have to do this. Okay, so that was part 3. And part 4, that one is very simple. If f of x is written as a power series, let's say, c sub n x to the n from 0 to infinity, then we can go ahead and simply derive both sides. Remember, f was differentiable of any order, right? So then f prime of x, which you might think, like, how the hell are we supposed to take the derivative of this? You can go ahead and take the derivative one term at a time. So you can do term-wise, meaning that's simply summation n from 0 to infinity, okay? So it's, what is the derivative of x to the n? The derivative of that is n x to the n minus 1. So it's going to be n c sub n x to the n minus 1. Now, one thing happens here, and that is, first, your first term is 0. You're going to have to start your series with n equal 1. Okay? Let's see what the second derivative. So second derivative is derivative of that guy, okay? Derivative of that is n times n minus 1 c sub n x raised to n minus 2. And what value do I start my series with? Think about it. If I start 0, it's 0. If I start 1, that makes it 0. So I have to start from 2. Okay? Let's do another one. The third derivative of that is n times n minus 1. Derivative of that is n minus 2 x to the n minus 3. And c sub n, this time you start from 3 to infinity. Why doesn't Cn drop out if it's constant? It's constant, so it's like multiplied by. I'm not taking the derivative of this. It's like you're taking the derivative of 7x to this, not 6. Let's do, a different number. What's the derivative of 7x to the 11? Well, sort of ignore the 7. Take the derivative of x to the 11, which is 11 times x to the 10, and then we multiply this by 7. So c sub n, since it's a constant, you're right, it's a constant. So you simply multiply it each time you take that. Right? If it was summation, derivative of c sub n would be 0 with respect to x. Does that answer your question, Eli? I can try again. Different way. Okay. Then, of course, you can integrate, right? So integral of f of x dx is simply, you can, again, integrate one term at a time. Cn is a constant, so x sub n dx, and starting from 0 to infinity, which is, c sub n x to the n plus 1 over n plus 1, and starting from 0 to infinity. Okay? So what I'm trying to say is that you can differentiate and you can integrate the power series, and that happens one term at a time, or term-wise. Okay. How much time do we have? Damn it. All right, we can stop right here. I'm not going to go over. So on Monday, when we come back, this is what I'm going to do, basically. An equation, differential equation is given. This is differential equation, okay? Let me do an example. Let's say y prime plus 3y equals 0. A very simple one. We already know how to solve this, so I'm just doing a simple example, okay? The unknown function is y of x. This y of x, in a very complicated cases, you cannot write it as an algebraic equation, algebraic expression, okay? So the assumption is we can represent this solution as a power series, okay? So to figure out what this function is, if you can recall, all we have to do, we need to figure out what these coefficients are. Because as soon as we figure out what these coefficients are, equivalently, we can identify the function itself. So we start by the assumption that the solution of this differential equation is a power series, right? Then we have to differentiate it, put it here. We have to put itself right here. Then we get two power series, and then we have to manipulate the coefficients of that power series to figure out, you know, the form of the coefficients. So eventually we want to figure out what exactly is CNRs. So that's what we'll do when we come back on Monday. Does the index not change for integration? I mean, no, because think about it. Let me write it down. I should have maybe explained this way. So this Cnx to the n, okay, is C0 plus C1x plus C2x squared plus so on. Okay, let's integrate. So what's the first one? It's going to be C1x, C2x squared over 2, plus C3x3 over 3 plus so on, which can be written as what we just said. So it's Cn x to the n plus 1 over n plus 1, n starting from 0 to infinity. And by n plus 1, n starting from 0, exactly these terms match up. It's only derivative where you have to change the index, but an integral, no, you don't have to. Okay, guys, we can stop right here. I'm going to go ahead and pause and stop the recording. Doesn't really have any questions.